Okay, so now we're going to continue with future memory reliability and security challenges. Of course, we're going to still spend some time on Rowhammer toward the end, since I would say it's the most immediate challenge that we're facing in main memory. And it's not going to go away, hopefully, based on the studies that I've shown you. It's clear that it's not going to go away, and we need a solution to it. And this sort of problems exist in industry. And hopefully I'm going to give you a historical perspective also, because some people thought this was not a problem when we first tried to publish our work, or a problem that's not going to be important in the future. Okay, so let's talk about the future. Essentially, hopefully I've given you a lot of data that DRAM is becoming less reliable and more vulnerable. This was not just Rowhammer, as you can see, but we've discussed this work briefly, where we showed this picture showing there's a huge correlation. There's a large positive correlation between the DRAM chip density and the server failure rate that we see in systems. And I would recommend reading this work if you're interested. I know I'm throwing you a lot of readings, but this is all, none of this is really required. This is something that you can do on your own if you're interested. If you're not interested, you can just ignore them, right? Clearly, due to difficulties in DRAM scaling, other problems may also appear, or they may be going unnoticed. This is something we warned of as early as 2012 when we were starting the Rowhammer research. Now, hopefully, we have a lot of evidence that some errors may already be slipping into the field. Some of them already have slipped into the field, like read disturb errors, which are a fundamental error mechanism in any type of memory. They have already slipped into the field. So something that should not have happened actually happened. Retention errors, as we discussed, that's a huge problem. And I believe some of them may already be slipping into the field, because this is such a problem. Testing for retention is in a sense similar to testing for Rowhammer. Maybe it's a bit easier because we have developed some mechanisms to test at high temperatures, for example, or reduced refresh intervals that can give you an indication of what happens at low temperatures and higher refresh intervals, or vice versa, lower refresh rates, let's say. So retention errors may be a little bit easier, but still they're not as easy because of variable retention time problem. Variable retention time problem introduces random bit flips. As a result, some of them actually may be slipping into the field also. The question is, can they be exploited? Clearly, they can be reliability problems if you're getting some retention errors in existing systems. Maybe sometimes my computer stops responding because I get a retention error in one of the DRAM bits, and as a result, the system hangs. It's possible, or system has to reboot. It's possible. I believe actually this is happening. Sometimes it's because of software issues, of course, but sometimes it's because of hardware issues as well. And this is not easy to detect clearly. In fact, there was this keynote in Dependable Systems and Networks conference, which is a major computer dependability or fault tolerance conference in 2014 by some software engineer at Google. He basically spent almost the entire keynote anecdoting how they spent 8 months or so chasing for a bug that they thought was a software bug in one of their software that's running in their distributed system, which turned out to be a hardware bit flip in main memory. Essentially, they chased for this bug for 8 months. It occupied a lot of people's times. And as a result, it made their system inefficient for some time because they had to turn off some things and not run some software for some time. And in the end of 8 months, they concluded that this was a bit flip in main memory. You can maybe find the slides of this keynote online. It's DSN, Dependable Systems and Networks 2014. If my TA is Hayu and Konstantinos, you can look it up and link those slides if they can be found online, of course, then even better. I remember that at least. Maybe it's not the entire keynote, but essentially that's what I remember being a key takeaway of the keynote. So basically, these issues, when they get exposed to software, yes, they may not cause security problems like as bad as Rowhammer potentially, but they may cause reliability issues. And in the end, even if you're a software engineer, you have to deal with them. And dealing with them is much, much more painful than dealing with a software bug although software bugs are painful, no question about that, especially some hard to find bugs in multi-threading, for example. But these take you to a different level. Okay, there could be other errors, read errors, write errors. You can read the paper that I mentioned earlier from my group on Facebook memory errors, for example. Clearly, these errors can be reliability problems, as I mentioned. They are real problems causing commercial software to fail and big companies to spend time to understand what's going on. And on top of this, they can cause security vulnerabilities, right? And this is the hardest part, security vulnerabilities. I mean, clearly, Rowhammer is causing a security vulnerability, but we don't know who's exploiting or who's not exploiting the field. Retention errors, somebody may have found ways to exploit them. Who knows? There are people out there who will actually go to very long lengths, let's say, to actually exploit some of these vulnerabilities to get not necessarily your data, but maybe even more important data out of the systems, right? Okay, so we've discussed the retention time failures in DM, and I think this is going to be worse, and we know that this is going to be worse scaling into the future, and I've given you some scaling results also, and papers that looked at the scaling of this. And clearly, I'm not going to spend a lot of time, but determining the data retention time of a cell or row is getting more difficult. And they may already be, these retention failures may already be slipping into the field. So DRAM manufacturer may say, okay, I've tested this DRAM chip at 64 milliseconds. It's going to work. There will be no retention time failures. But because of variable retention time in the field, you may get a retention time failure at 32 milliseconds, right? Or not maybe because the testing was not exhaustive enough. And as a result, you may get a retention time failure. So these could lead to security vulnerabilities potentially. And we've already discussed these. And this is the reason why DRAM manufacturers added error correcting codes, because they could not really profile for these retention time failures in the presence of variable retention time. And on top of that, on top of adding error correcting codes into the DRAM chips, they also reduce the refresh interval, meaning that increase the refresh rate. So the common refresh rate is 32 milliseconds today. And on top of that, there's in DRAM ECC. So basically, there are two ways that are actually making systems, I don't want to say necessarily more reliable, but constraining things such that you add more solutions to correct these errors. And even then, these solutions may not be perfect. Okay, so I believe actually there are a lot of retention times failures that may be escaping into real workloads, real systems, except these are harder to screen for. Okay, and you already know some papers that we have discussed. This is one of our early papers that talked about retention time failures. And you already know why this is actually more difficult than even what we discussed earlier. Basically, there's data pattern dependence and there's variable retention time. And if you're really interested, you can rewatch our lecture on data retention and refresh. And clearly for this type of thing, the industry has been writing papers. I've already referenced this paper many times. If you haven't read it, feel free to read it. Again, it's not required, at least yet. We may require it at some point as part of a homework. It's a 4-page paper. And this is why industry is worried that at least forward-looking folks in industry said it's a good idea to design controllers and DRAM together. Okay, so let me be a little bit more higher level, and let's talk about keeping future memory secure. And if you have some ideas here, feel free to discuss on Piazza. If you have time here, we can discuss here also. But basically, it's not just about DRAM also. I would like to emphasize this point. DRAM is clearly a majority of the main memory market. And when I say a majority, it's more than 99%. It's a huge majority of the main memory market. But there's also a storage flash memory we use. And some people are trying to make flash memory really fast such that it can replace parts of DRAM at least. That's interesting. And there are clearly some emerging technologies we have discussed, and we're going to discuss even more going into the future, that are going to be either replacing part of DRAM or augmenting, or replacing part of flash memory or augmenting. Basically, they can actually be even on chip. Some of them can be even replacing on chip L3 cache, for example. STT-MRAM, for example, is a good candidate for it. So basically, these memories are all vulnerable to errors. I've talked a lot about DRAM, but all of these issues that we discussed, retention, exist in flash memory. I mentioned that briefly last time. Redisturb errors exist in flash memory. If we have time at the end of this lecture, which we will not, we're not going to discuss the redisturb errors in flash memory, but leave it for later. And emerging technologies have even more error mechanisms. So phase change memory, for example, is vulnerable to write disturb effects. It also has retention shifting, resistance shift, or resistance drift phenomenon, where resistance drifts, very similar to retention loss. So they also have redisturb effects, etc., etc. I'm not going to go into all of the issues related to these memories, but basically we have a huge problem with memory reliability and security because all of these technologies are scaling down to low nanometers, hopefully less than 10 nanometers. Well, hopefully, because it buys benefits, right? If it buys benefits, we should scale them. Okay, some of them are going to three-dimensional. So flash memory today is three-dimensional, for example. That was a big breakthrough in flash memory in the last 5 years or so. Manufacturers figured out, instead of reducing the size of a flash memory cell, we could actually string together flash memory cells in a three-dimensional manner. And that actually increased the capacity, but three-dimensional memories actually have their own error mechanisms. Now you can actually have layer-to-layer variation. You can have different effects between different layers, etc. And also, I think some of these, like 3DX point, Intel's 3DX point, which is based on phase change memory, is also three-dimensional. There's a reason why it's called 3DX point, right? 3D cross point. Okay, so basically we have a huge problem with memory. And we've already discussed DRAM, but keep in mind that the issues, I like discussing this real problem that we have at hand, that we have a lot of evidence for, but that's true for flash memory also. And that's less true for emerging memory technology. We do not know exactly their error mechanisms yet. There needs to be more research done in this area. And it's not easy research to be that is being done, but there's a lot more to be done over here. So let me give you an example. This is based on a paper that we had written on flash memory. I actually flashed it last time. It's basically based on 8 years of research that we've done on flash memory, and we were invited to write a survey on how do SSD errors happen and how do they get mitigated. On these columns over here give you the error types, but you can see some of them are data retention errors, some of them are cell-to-cell interference errors, different from redisturb. Some of them are redisturb errors. Some of them are programming errors. While you're programming, writing something to a flash cell, you get errors. Some of them are endurance errors. These are called program erase cycling. It's a fancy term in flash, but as you keep writing to a memory location in flash, you wear out. They're called wear out errors also, essentially, endurance or wear out errors. And you can see these errors are real, they exist. In DRAM, wear out is less of a problem, but it may be becoming a problem as with smaller technology nodes. We don't know yet, but clearly in DRAM, data retention is a problem. Redisturb is a problem. Other types of cell-to-cell interference is a problem. Program is, in DRAM, there's no programming operation. It's really writing to DRAM. And write errors also happen in DRAM. So except for wear out, which may be happening, we know that all of these errors happen in DRAM also. So it's not special to DRAM. It's not special to flash. It happens in flash also. So similar errors. So what we're missing here is write disturb, which is categorized over here. Write disturb, whenever you're writing to a cell, you also disturb other cells. So it happens, it's categorized on those cell interference over here. So you could actually make this even more finer grained. But these errors exist, and there are mitigation mechanisms, as you can see. And this paper discusses essentially the whole matrix over here. And clearly there's literature. These are the references to different literature. So we're aware of these errors, but they're getting worse, and they may be slipping into the field in flash memory also. So the key question is basically, how can we have principled designs? And I always argue for principled designs. If you've taken my digital design and computer architecture course, you know this. It's good to find some principled design. Somehow, we would like to design fundamentally secure computing architectures and predict and prevent such, against security, safety, reliability issues. And I put safety over here because, again, a bit flip can be a reliability problem, a security problem, or a safety problem. If you get this bit flip that you haven't accounted for while this airplane is flying, well, too bad, right? It could be very, very costly and fatal in those cases. Okay, so I think again, I don't have the solution, but I think this is the solution direction that we're advocating for. I think we basically have a 3-step thing that we need to go through and iterate over. First of all, we really need to understand what's happening. And I think that Rowhammer happened because industry did not understand what is happening, or even if they did understand, they didn't think it was a big vulnerability, right? Basically, if we had understood early enough that there is some vulnerability that's coming up, and if we had discovered it early enough, we could have provided some mitigation or solutions by architecting well, and by also doing design and test much better. And understanding also comes with design and test much better. Basically, you need to design and test very well such that you can understand better. So these things are related to each other. But basically, I think the first step is really somehow understanding. Somehow we would like to model and predict what will happen, what kind of errors we will see, what kind of vulnerabilities they will cause based on real device data and analysis. Of course, it cannot be fully based on real device data. Real device data is a good way of seeding the vulnerability modeling, like we have done in the 2020 paper in revisiting Rowhammer. We need to somehow analyze it also, basically. You need to do it, analyze it with simulations, and that could lead to the understanding of vulnerabilities and how bad they will be. And I think our revisiting Rowhammer is one good example of understanding. Our earlier Rowhammer paper is another good example of understanding. Basically, they basically show there's a vulnerability and how bad it will become. And of course, I think we would like to develop reliable metrics to assess how bad something will become. And I think the papers that I mentioned, like HC first, hammer count first, is a good metric, but there could be many other metrics. Some metrics could be exposed to software potentially. I think there's a lot that needs to be done over here for understanding. Okay, that's the first step. And I've already discussed understanding, but the next step is architecting. So how do we actually design principled architecture with security as key concern? Basically, I think we don't know the answer. We know perhaps how to understand, maybe not fully. We know less about this architecting part, but I think we need to have good partitioning of duties across the stack. We cannot insist that something always gets corrected in the memory controller or main memory or software. We really need to rethink this entire stack and have a good partitioning. Of course, while doing this architecting, we cannot give up performance and efficiency. And I believe we need to consider patchability in the field, because clearly we're not going to be able to find out all of the errors as easily. Of course, we should do due diligence and we should do modeling and understanding really well. But there will be some errors that are happening that are found out after we manufacture the devices and the memory controllers. If we had some sort of patchability in the field where we could upgrade the software or the firmware that runs on these devices such that we can actually solve the issues like Rowhammer, for example, after they're discovered, we would alleviate the problem much better, basically. I think this sort of patchability is really important. That's why I think configurable or reconfigurable memory controllers and memory devices are going to be even more important going into the future. Okay, on top of this, I think we need to know how to design and test. We need to have principled design, automation, and online testing mechanisms for Rowhammer, for example, but also for retention times. And we need to design for security. Basically, hardware design for security is an area that's important, critically important today. How do we design things for security to to basically account for unforeseen circumstances, right? And I don't think we have good answers, full answers for this yet. But I think patchability in the field is one answer. I think patchability is a design for security. But I think testing, online testing methods that are good and that can be employed in the field while the system is running at low overhead, that's also helpful for design for security. Automating ways of understanding and finding for errors is also a good design for securities. For example, from that perspective, Trespass is a testing tool, good testing tool that can enable better designs for security. So you can imagine many things over here. And of course, this needs to have high coverage. You cannot design a tool that's not good enough, right? If it discovers everything, that's great, right? Also, online testing needs to have high coverage, low overhead, etc., etc. So clearly there's a lot to do over here also. And design and test actually spans the entire stack. Architecture also spans the entire stack. So these are cross-stack, going from potentially algorithms all the way to devices. Although I'm not sure about the algorithms. I don't know if you really want to expose errors to algorithms, but there are some fundamental algorithms that do not care about errors, that are resistant to errors. Those are always good to develop. But clearly you cannot bank on all of the algorithms being resistant to such errors. So you cannot basically say, okay, I have memory that's errorful, don't deal with it. I don't think that's a good solution. At least you need to design some heterogeneous memories, as we've discussed, that have different types of error rate guarantees. And then the software can be designed to adapt to these different memories. Okay, so this is the three directions that are also discussed in some of the papers that are recommended. But I think understanding requires clearly designing systems like this, where you can test things well. And we have done it for years right now. There's more to be done in this area. So this is how we understood and modeled for flash memory, for example. And as I said, flash memory itself actually has a lot of potential areas. And this is the paper that I mentioned that I would recommend based on our 8 years of research. And there's an updated version also that, unfortunately, I don't have it in the next slide, but there's an updated version that appears in Inside SSD Drive's book. Okay, and understanding flash memory reliability is, there's also another way of understanding reliability, which is doing large-scale experiments, right? Small-scale experiments are like this, are very nice, where you have an FPGA-based memory control and you understand every single error mechanism and figure out how to solve it. But large-scale experiments in the field is also very useful. And we talked about some large-scale DRAM experiments, but there are similar large-scale experiments that can be done for flash memory, because SSDs are employed in data centers. And this is one experiment that we have done together with the Facebook again, in terms of how the flash memory failures occur in the field, what are their characteristics, are they correctable, not correctable, under what conditions they become worse, what are the effects of the workload, et cetera, and you can read that over here. Because, and we've done it again on all of the data centers, on all of the machines on Facebook's data centers that use SSDs. Not all machines have SSDs in the data center, but a good chunk of them today have, and I think in the future all of them will have. But basically, this is again based on very large data sets. And I think it's fascinating to do these studies as well. But these are all for understanding again. And in the end, NAND flash memory have vulnerabilities also. So in this paper, we discussed some vulnerabilities due to programming mechanisms, because programming mechanisms actually induce errors in adjacent cells, similar to Rowhammer. There are some potential vulnerabilities that happen, and there's some potential exploits. Of course, this is not as easy to exploit as Rowhammer, because Rowhammer directly exposes the bit flips in your data structures. Here, the bit flips are exposed somewhere in files. And the key is how to exploit that. Clearly, you cause corruption, which is not good from a reliability perspective. So this is clearly a reliability problem. But it remains to be seen if this is also an exploit that can be exploited at higher levels of the software stack, because there are a lot of levels of mapping of a file from the software to the operating system to the SSD controller to internally in the flash device. So there are a lot of levels of mapping that actually may not make it easier. And there's a huge decoupling actually that happens between the operating system and the SSD storage device today, which may change going into the future with new technologies, because with new technology, you cannot afford so slow mapping mechanisms that we have been used to. Okay, and as I said, 3D NAND flash is important, and it's three-dimensional. So three-dimensional NAND flash actually has new reliability problems. And in addition to inheriting the old reliability problems that happen with planar or two-dimensional flash. Again, I'm not going to go into the detail right now, but this shows you that the technology is becoming worse and worse, and we really need to understand it. And 3D has different properties than 2D, and it may become worse going into the future. And you can see that retention is becoming worse actually in 3D NAND flash memory, even though the size of a cell is becoming larger because of there's some phenomenon called early retention loss in 3D NAND flash memory. Okay, I'm not going to talk more about this, but let me get back to the fundamentals a little bit. Basically, I started the lecture, memory reliability or Rowhammer lecture, with this and said bit flip is not good because our infrastructure depends on it, right? And I still believe this. I think it's really important. Our infrastructure really depends on bit flips, and especially something like main memory having bit flips that are uncontrolled is really unacceptable for a safe and secure infrastructure and a reliable infrastructure. But okay, let's go through the analogy of bridges. This was Galloping Gertie, which is the Hood Canal Bridge. By the way, you cannot cross this bridge right now. What happened was after this bridge collapsed, they constructed two bridges, one going this way and the other going back this way. Now, it's nice. Now they have two bridges. Hopefully, they're not vulnerable to this aerostatic flutter that the bridges were vulnerable to. But now they have a reliability solution that's commonly employed in modern systems, right? Now you have two bridges, and if one of them falls, you can go through the second one. So it's called dual modular redundancy, basically. It's very similar to this Tesla chip that I showed you earlier. You have 2 chips in the Tesla board so that you can tolerate some of the safe problems. Okay, so these bridge failures are actually not old. This was 1994 in Seoul in South Korea on the Han River. Unfortunately, this bridge failure actually caused a lot of deaths. And there are other reasons, of course, for this failure, but this bit flip actually causes problems, as you can see. This is in Minneapolis on a busy highway in 2007. And this also caused some deaths, which was not good. And the more recent one is in Genoa in Italy, very close to here. This, I believe, also caused some deaths. So not all of the bridge failures are non-fatal, like the Hood Canal one. And these keep happening. And it's interesting to see that, I mean, human beings have been constructing bridges for thousands of years, and we're still not perfect at it. So there's a fundamental reliability problem, clearly, that happens. Or somehow we're not taking into account every single problem when we construct the bridges. You can speculate on this. But in the end, somehow we're not able to circumvent these. And unfortunately, bridges are much more difficult to prevent, I think. Once something like this happens, you need to reconstruct it. If you want to reconfigure it, well, it's a lot of overheads in bridges. But in computing, here where the analogy is to the favor of computers, right? You may get a bit flip like this in computing, but if you already have accounted for the possibility of a bit flip, if you had patchability in your memory controller or DRAM device, such that you could route around the bit flip, or if you could correct the bit flip, if you could change the memory control algorithm such that you do more refreshes intelligently, you can avoid such failures. So basically, I think the takeaway is in computing, it's much softer compared to what we have in real hardware. So computing is hardware, clearly there's a hardware component. But that hardware component is still softer than the hardware component that you have here because you can add reconfigurability, patchability to it. You can add more hardware, yes, and some of it will be used for reconfiguring, reprogramming, changing the firmware. And that's the idea over here. I think this is a very good direction in computing today. So let me give you some final thoughts on Rowhammer, and then we're going to take some aside so that we can discuss some review-related issues. So basically, this is actually a slide that I borrowed from Satya, who teaches distributed systems at CMU. Basically, after Rowhammer, he basically added Rowhammer as one of the 3 examples he uses for Byzantine failures. So if you've taken the distributed system course, you may know what Byzantine failures are, but I'm going to describe that basically in a little bit. These failures are characterized by undetected erroneous computation. They're opposite of fail fast. Basically, fail fast is a property that you want. If you have a failure, you would like to either get no result or fail with an error. That's fail fast, and that's good. But unfortunately, you cause erroneous computation with a bit flip in Rowhammer, and erroneous can be used for malicious. That's the intent is really the only distinction over here. And it's very difficult to detect and confine Byzantine failures, unfortunately, has been proven for years and years. You should really do all you can to avoid them. And if you're interested, Byzantine failure problem was exposed by Leslie Lamport, who's a Turing Award winner, as early as 1980s, as you can see. And I copied the abstract over here. And I'll actually go through this and read it because it actually builds on another analogy. I'm not going to go through the paper, but I would recommend it. But basically, you can see that it targets reliable computing systems that must handle malfunctioning components that give conflicting information to different parts of the system. This situation can be expressed abstractly in terms of a group of generals of the Byzantine army camped with their troops around an enemy city. Communicating only by the messenger, the generals must agree upon a common battle plan. However, one or more of them may be traitors who will try to confuse the others. The problem is to find an algorithm to ensure that the loyal generals will reach an agreement. It is shown that using only oral messages, this problem is solvable if and only if more than 2/3 of the generals are loyal. This doesn't sound good, right? You really want a 66% loyalty majority. So a single traitor can confound 2 loyal generals. With unforgeable written messages, the problem is solvable for any number of generals and possible traitors. Applications of the solutions to reliable computer systems are then discussed. So basically, there are people who develop Byzantine fault tolerance protocols, and they essentially, if you really want to be tolerant to faults in the general case, you over provision your servers. You buy 3 servers where at least 2 of them trustworthy in the end. So basically, you're over-provisioning your service. Anyway, you can take a look at this paper. I would recommend it, but we don't have time to go over it in general. But let me revisit Rowhammer, and then I'm going to take some time to talk about some of the interesting comments we got in our original submission of Rowhammer. So I've already said everything I said over here. It's the first example of a simple hardware failure mechanism that can create a widespread system security vulnerability. So this has enabled a new mindset in the security community, especially, and a renewed interest in hardware security attack research, which basically show that real memory chips are vulnerable in a simple and widespread manner. This caused real security problems. And hardware reliability and security connection became a mainstream discourse now. As a result, as I've showed you, many new Rowhammer attacks got developed, maybe more than 100 papers in top security venues. There's more to come, I believe, as Rowhammer is getting worse. And now Trespass has shown that existing mitigations don't work. And there are many new Rowhammer solutions. Apple security release was one of them. Memtest 86 updated was a potential solution. And many solution proposals are there in top venues. Latest in ISCA, actually the slide is old, I think. Latest is really in ISCA 2020, I believe, and Micro 2020, actually. There's one that's coming up. And I believe principled system DRAM co-design is a good solution direction. And I believe there's more to come in terms of solution direction, especially architectural solution directions. But keep this in mind and contrast this with some of the review comments that I'm going to share with you later on. But perhaps most importantly, it enabled a shift of mindset in mainstream security researchers. General purpose hardware is easily fallible in a widespread manner. Its problems are exploitable. And this mindset enabled many system security researchers to examine hardware in more depth and understand hardware's inner workings and vulnerabilities. As a result, I believe it's no coincidence that 2 of the groups that discovered Meltdown and Spectre heavily worked on Rowhammer attacks before. And you can take a look at who those 2 groups are. And I believe there is more to come in terms of hardware vulnerabilities. Now that the cat is out of the bag, I think there's a lot more going to happen in terms of hardware security research, in terms of figuring out what else is vulnerable in our mainstream hardware and how do we solve the problem. And I think this is really critical to do, because this is really what enables a better infrastructure. Better infrastructure doesn't come from sweeping the problems under the rug, saying that, oh, we solved the problem, or trusting something that has proven non-trustworthy, by the way. Maybe you trust once or twice, okay, but if someone proves that they're not trustworthy, it's probably not a good idea to trust them going forward. And I see the DRAM industry like that at this point. Unfortunately, they're guilty at this point. Maybe in the initial part, they were not guilty, but if you do repeat a mistake many times, then at some point you become guilty. Okay, but I think as research, we really need to understand these things and basically find these problems that are happening, whether or not it's known by industry, right? And some of these things are not known by industry. For example, I believe Meltdown and Spectre were really not known by industry who implemented high performance processors. Okay, so let me summarize, and then we're going to take a short detour. So DRAM reliability is reducing. Reliability should open up new security vulnerabilities. They're very hard to defend against. Rowhammer is a prime example. As I said, it's the first example of how a simple hardware failure mechanism can create a widespread system security vulnerability. And I believe its implications on system security research and also architectural solution research are tremendous and exciting. There's bad news. Rowhammer is clearly getting worse, and it's not sold despite it's advertised that it's sold. But there's good news also, which means that as engineers, researchers, people who want to progress in the field, we have a lot more to do. We are now fully aware hardware is easily fallible. We're developing both attacks and solutions, and we're developing principled models, methodologies, and solutions. And if you want to be any part of any of this, feel free to reach out to me and any of the TAs, especially those who have worked on Rowhammer. So clearly, you can learn more on Rowhammer from these papers. The retrospective is very useful, hopefully, because we spent a year to write this paper, and it's based on our experience for many years, clearly. But these 2-3 papers in 2020 are important as well. Now, let me give you some history, because I think hopefully this will be instructive. Some of you may become researchers, some of you may become people who propose, do some evaluations in industry and want to convince others. And eventually you'll get reviewed, basically. You have this cool observation and you want to put it out into the field such that everybody understands the coolness of it, right? Sounds good, right? But it's not always nice as that way. Basically, I already said this many times, Rowhammer clearly led to a large body of work in security attacks, mitigations, architectural solutions, and who knows what else. And work building on Rowhammer still continues. There are solutions in Micro 2020. There's work in ISCA 2020. There's actually, I didn't put security and privacy 2020. There's a lot of work. There's a session on IEEE security and privacy titled Rowhammer, for example. There are 4 papers in that session. 2 of them are from us, but 2 of them are from others. But when we first put it out into the field, it was initially dismissed by some reviewers and it was rejected from a top conference, Micro 2013 conference. And I'm not ashamed by it because I don't think it was fully our fault. I believe we actually did due diligence, but reviewers did not really understand. And as I will show you in a little bit. And this happens commonly in science, actually. Look, you can see over here. I apologize that I'm going to take a little bit more time, but since we've been taking more time, what we're going to do tomorrow is we're not going to have a lecture, and we're going to allow you to actually work on your labs tomorrow. Feel free to ask questions on Piazza, etc. So there's going to be no lecture tomorrow. So you have the full 3 hours to yourselves. But basically, okay, let me go back over here. That was an announcement in the middle of something interesting, which is these are the 6 reviews that we received when we first submitted the paper in May 2013, as you can see, to the conference Micro. And you can see that some people liked it. 5 is a good score. I think it's a strong accept. 4 is an accept. But 4 reviewers said, oh, it's a strong reject. I don't want to see it in the conference. 2 is not a good number also. It's a weak reject, but still it indicates that I don't want to see it in the conference. And you can see that was rejected. And you can see that the novelty is actually deemed very high. 4 is actually the highest number, I think, over here in terms of novelty score by reviewers, even some of the reviewers that even say it should be rejected. And writing quality is high, and some reviewers think that they're experts. So let's take a look at this a little bit more, because I think this indicates something that's not very healthy in the field, not just in computer science, not just in computer architecture, more generally in computer science, but even more generally about computer science plus engineering, and even more generally in science and engineering itself. I'm going to close with some examples also later on. But basically, you can see this review, that's a reject. It says even though it's a new contribution, it's well written, it's rejected. Basically, it says, okay, you show this happens at DRAM array, but you don't show this in a realistic DRAM usage scenario. And I'm going to show you our rebuttal to it. This reviewer expects a bit too much, in my opinion, because he or she is dismissing that this could be a security concern. And in fact, we say that in the rebuttal, this is really a security concern. You should pay attention to it. Yeah. And also the second one over here says lacks architectural, microarchitectural impact on, which is not necessarily correct. But you can a little bit read over here because it's interesting. I found the paper well written, very well written and organized, easy to understand. The topic is interesting and relevant. However, I'm not fully convinced that the disturbance problem is going to be an issue in a realistic DRAM usage scenario, main memory with caches. In that scenario, the 64 millisecond refresh interval might not be enough. Overall, the work presented, the experimentation, and all of these spelling errors are not mine, they're copy and pastes from the review site. And the results are not enough to justify and claim that DRAM disturbance may not be an issue for future systems and that microarchitectural solutions are required. Basically, it's very dismissive, as you can see. This reviewer strongly believes that this will not be an issue and microarchitectural solutions are not required. And then I really encourage the authors to address this issue, to run a new set of experiments. If the results are positive, the work is great and will be easily accepted. So this is a good reason for reject, as you can see over here. Test scenario in the paper, which is a security attack scenario that is used to create disturbance, is not likely to show up in a realistic user scenario. So basically, I think of this review as very narrow-minded. Yes, realistic user scenario, we never proved, basically, in a real application. We never show that this occurs in application X that's run. Although there are some cases that I've seen in industry under NDAs that I cannot really show that these actually happen in real applications also. Of course, it's a much more less common thing to happen in a real application. But this reviewer is dismissing the possibility that security is real. Basically, I think if I summarize this review, I say security is not realistic. And it's a very terrible mindset from a reviewer perspective. I would never want to be that reviewer myself, and I try hard to be not that reviewer who is not open-minded, as you can see. And I think in this case, most people in the world would agree that security is real, right? So you can see our rebuttal. I just put an excerpt over here. We say malicious workloads and pathological access patterns can bypass, trash the cache, and access the same DRAM row a very large number of times. While these workloads may not be common, they're just as real. So this is basically a security concern. And clearly our rebuttal was dismissed. In the end, the paper was rejected. So the reviewer A, who's an expert, also says, yeah, I think this is not very also great, basically. To make sure that correct information and messages are given with the research community, it would be good if the conclusions are drawn in the paper were verified with the actual DRM manufacturers, et cetera, et cetera. Basically, knowing the technology now would be nice. In the end, maybe these were not the reject reasons, but we actually had verified with the DRM manufacturers our results. Okay, so reviewer C, let's move on to the next reviewer. This is also a weak reject. As you can see, it's not as strong as the previous one. But basically, the rejection reason mainly is this is an excellent test methodology paper, but there is no microarchitectural and architectural content, even though we talk about solutions like Para. Okay, basically, this reviewer predicts that this will not spur on future work because it doesn't have architectural content. Well, I think the history speaks for itself. And reviewer C, again, says, leave it to the DRM vendors, basically, which is probably not a good idea, as you know, after the 6 years of research that we have done, right? Basically, the authors have identified a contemporary disturbed sensitivity in DRAMs, but as non-technologists, I don't know why he or she thinks himself or herself or ourselves as non-technologists, our community can generally only observe, not correct such problems. This is a terrible mindset again, right? Basically, this is saying, leave it to the DRAM manufacturers. And it's an expert in the area saying that. So hopefully this gives you also an example of the mindset that we've been dealing with and why this has not been solved as well, because this is coming from a reviewer of a research paper who's supposed to be extremely open-minded and should accept an excellent paper that they deem excellent, right? But they're coming up with these extremely speculative reasons. Okay, I don't care about the solution basically. Somebody else should solve the problem. Leave it to the DRM vendors. Hopefully this gives you an idea that the mindset is terrible, including in academia as well as industry. Of course, this is not to paint a completely bleak picture to you, because clearly there are some reviewers who accepted the paper also, but there are some reviewers who have this mindset. In my opinion, they should not be allowed to review papers, frankly. I would go as far as that, because this is completely unfair. And as a result of that, research gets delayed. Okay, so reviewer D gives a strong reject, as you can see over here, and basically says there is nothing new in Rowhammer. I mean, that's my, of course, rephrasing of everything over here. Basically, it says the mechanism investigated by the authors is one of many well-known disturbed mechanisms. This paper doesn't discuss the root causes. Overall, I find nothing new. You can read the rest over here, basically. Okay, as a result, the novelty is insignificant, as you can see, right? And this is also an expert in the area. Again, this is an unfair review, because clearly in the paper, we mentioned all of those read disturbed mechanisms, actually. We say that those read disturbed in the rebuttal, which I don't want to bore you with over here, but I'd be happy to share it if people are interested. I think it's good to share this information publicly, such that people see that there's something wrong in the review process and there needs to be more accountability. Because clearly this reviewer got away with whatever they said, right? And the paper got rejected. Basically, in the paper we acknowledge, and in the final paper also, we acknowledge that there are many read disturbed mechanisms. What we show is not a read disturbed mechanism. What we show is an analysis of a read disturbed mechanism that has slipped into the field. And we show an analysis of how it has slipped into the field, and no one has really recognized it. And a detailed analysis of it. Basically, the reviewer is missing that part. And even though we rebutted it, in the end, this didn't change the view of the reviewer, and the paper was rejected from this conference. But the good news, as you can see, is the paper was accepted in the next conference, even though it was delayed for at least 6 months. So this next submission is in 2013, and the conference happens in 2014. And basically, you can see that 4 reviewers out of 6 give actually very strong scores. 8 means award quality, actually. 7 means very strong accept. 6 means strong accept. But 2 reviewers, one of whom deems themselves an expert, actually give a weak reject. I believe this is a weak reject, and this is a reject, outright reject. One is a really strong reject, basically. So you can see that even the second submission, we got some reviewers who did not want to accept the paper. But overall, hopefully the reason prevailed and the paper was accepted clearly, and the history remains. But let me look at the reasons of this reviewer D over here, basically. So basically, the reviewer says, okay, correctly characterize things maybe. And strengths are actually scarce. As you can see, the author demonstrate the problem using real systems. It's a known problem, basically, the reviewer says. What you demonstrate in this paper is so-called DRAM Rowhammering issue. You can find even a paper in the YouTube video. Actually, we did this work even before that YouTube video was released. And if the paper was not rejected by the previous conference, this YouTube video would not have been there and would not have been used as a reason for rejection at this point. So it's interesting to see these reviews, as you can see. Basically, this is I don't know if I have the rebuttal put out. Let me see. I have the rebuttal later on. Okay, I'm going to get to the rebuttal, I think, at some point. But basically, we say that, oh, this is a video by a DRAM testing vendor, and it's a commercial video. It doesn't really go into the Rowhammer. It does talk about Rowhammer because clearly industry at this point knows about it because we talked about it and the paper is rejected. But it doesn't really go into the details of Rowhammer. Okay, but let's take a look at this. It's a well-known problem, and there's a video. And this is also very interesting. The relevance of this paper to ISCA is questioned. Basically, I feel this is more relevant to testing and dependable systems, but even then, I don't feel it's relevant. So it's a very good reason for rejecting papers, basically. Okay, let me go over the rebuttal very quickly. Unfortunately, it's not formatted well because it's a PDF, but you can also read it by yourself. It's true that different coupling phenomena have been observed. But there's a clear distinction between circuits and testing techniques confined to the foundry versus characterization solution of a problem that's out in the field. And the reviewer actually gave us 3 citations. That's old, but they do not demonstrate disturbances that exist in DIMMs that are sold then or now. Basically, there's no real data in those papers actually, let alone any large-scale characterization from multiple manufacturers. They do not construct an attack. They do not provide any solutions. And we already actually referenced all of those citations, and they're more related equivalent. So this is our rebuttal, hopefully telling the reviewer that you're really being unfair, right? It's a bit frustrating to get these reviews, especially as a PhD student who is doing good research, right? And then the expert in the field says, oh, okay, it's already been done, doing a sloppy job or doing a malicious job to actually prevent publication. And this is the rebuttal, and this rebuttal, I don't know if it worked on this reviewer, but clearly it worked on the committee, and the committee accepted it. And you can see the rebuttal for this video. Basically, we were aware of the video from Teledyne, and we already referenced the slides from the same company, actually, in the paper that was submitted, which this reviewer reviewed and decided to ignore this particular reference clearly. In terms of their content regarding Rowhammer, the video and slides are identical. All they mention is that aggressive row activations can corrupt adjacent rows. They then advertise how their test equipment is able to capture a timestamped DRAM access trace, which can then be post-processed to identify when the number of row activations exceeds a user set threshold. Both the video and slides do not say that this is a real problem affecting DIMMs on the market now. They do not provide quantitative data, nor real system demonstration, nor solution, which our paper clearly does. Okay, so let's take a look at the URE. This is a weak reject, as you can see over here. Sorry. And basically the same reason. It appears to be well known. Industry has already solutions to the issue, et cetera, et cetera. And then basically they say there are numerous patents citing the issue. You can see this patent over here. We actually referenced some of those patents in our paper, interestingly. And clearly we worked with Intel as early as 2013, who was filing patents on the topic. And basically they say the patent application sounds similar, blah, blah, blah. And you can see that, again, my overall feeling is that reliability characterization is important and interesting, but better target audience should be somewhere else. So don't bother me with this. Go and publish somewhere else. This is, again, a very bad mindset. It's not inclusive, as you can see. But again, our rebuttal said Intel made public, Intel patents were made public. Yeah, basically after our paper was submitted, Intel patents were made public. And the 2 patents are really not describing the solution that we describe, ... And there are limitations to the solutions. And patents in the end really do not provide any evaluation if you go and look at the patents. Okay, nevertheless, I think we were able to induce, even in the presence of those patents, existing Intel and AMD platforms show errors like we have discussed earlier. Clearly, patents don't provide quantitative characterization, nor do they prevent the errors. And we cite the patents. So you can read the rebuttal. Hopefully it'll be useful for you. I do not have enough time because I actually need to go and teach the next lecture right now. But if Mohammed is on the line or somebody is on the line, you can basically tell the students I'm going to be a bit late and we're going to not cover a lot of things anyway in that lecture today. So basically, I think before I conclude, this is a slide that I presented when I received an award in the ISCA conference last year. I basically told the reviewers, and these are things that I keep in mind when I review papers. It's important to be fair and very open-minded, because you do not know it all in the end. You cannot say, oh, this is not a real problem. How do you know? You can just evaluate the paper in terms of its technical strength, correctness, but don't speculate on whether it's going to be a problem, whether it's not going to be a problem, etc. So the previous things were all speculations, right? Clearly, the paper is excellent according to them, but they do not believe it's a problem. Now, this is very, very subjective, right? And clearly, history has proven them wrong, completely wrong in this case. That's why I can actually come and show these slides to you, right? You need to be open-minded because you don't know it all. Again, when you're reviewing papers in this course, I would like to ingrain all of these principles to you, because I believe these are really important for things progressing positively going into the future. Science progressing positively, engineering progressing positively, solutions progressing positively. And as a result, things progressing fast. Again, be accepting of different research methods. There's no single way of doing research. A couple of these reviewers, as you saw, more than a couple actually said, okay, this is test methodology. I'm an architect here. I don't care about this, right? This is really terrible mindset, right? As we've discussed, architecture should really span a large part of the computing stack. And on top of that, this is not even true. It's not a just test methodology paper. We propose architectural solutions to the problem, right? And some of the reviewers said, oh, I don't believe that this is going to spur on future work because architecture is not the place to solve the problem. Basically, they're not being accepting of different research methods. They have a fixed mindset. It's like a horse with blinders on, right? You don't see anything outside of your frontal view, right? Your blinders are on, you're like this. You cannot see anything that happens here or that happens here, right? So basically, this says, don't be a horse. Don't be a horse with your blinders on, right? So it's really important, I think, to keep this in mind. Again, there's no single way of doing research. Something that you may not really consider being a problem at this point or not requiring an architectural solution at this point, keep that speculative thought to yourself and just evaluate the paper as it is, and since it's providing a solution that works. Again, I think being constructive is extremely important. You can see, hopefully, see through the reviews and see how destructive some of those are, because they're not fair, they're not open-minded, and they're not accepting. And I think on top of this, there are other issues like having double standards. This is actually really interesting. I would recommend reading The Structure of Scientific Revolutions by Thomas Kuhn on this, something that I mentioned in an earlier lecture, because he also talks about this double standards and saying that some people just want to reject papers so that their papers get in, let's say, or their big mindset in terms of research doesn't get disrupted. So Rowhammer is very disruptive, clearly, because it basically shows that real chips are vulnerable. And clearly there are people in the world who may be reviewing the papers. Some of them could be from the DM industry. Some of them could be doing research, banking on the fact that DM is real, and they don't want to accept this fact, right? So I think there's a big conflict of interest that happens in the review process. And as a result, people knowingly or unknowingly have these biases that lead to double standards. And this is very dangerous, in my opinion. As a result, doing this blocks or delays scientific progress for non-reasons. And basically, I called out on this in my talk, and I said, let's be more fair, open-minded, inclusive, constructive, and not have double standards. Understand our biases, whether they're explicit or implicit, and not have them, basically, or have the biases, but not don't enforce them on everybody else in the world who will be affected by it. Okay, so if you're interested, I would recommend watching these interviews that I mentioned early on. This is an interview that talks about some of these issues, and this is my award speech where I actually flashed a slide and talked about it, and some other slides as well. So there are more thoughts and suggestions that I have. Clearly, you can watch those. But the book that I recommended at some point, The Art of Computer System Performance Analysis, essentially talks about these issues also. Basically, there will be decision makers, people who are accepting your ideas and papers. And again, I'm talking about this because you may become a researcher, you may not become a researcher, but you, I believe, care about this because you will be presenting ideas, new thoughts, new analyses to people who will be making decisions based on them, and they may dismiss you. Very similar to the comments that we have gotten. They may dismiss you for a gazillion reasons, as you can see in this slide. Basically, even if you do everything correctly, this may not be enough to persuade your audience. because audience may actually have more things to complain about. Workload, this is not realistic. We got that comment. Metrics, this is a test methodology paper, right? You don't show it on a realistic usage scenario. Configuration detail. There are lots of details actually in the reviews, you can see. So there's no end-to-end analysis. And as you can see, there's no clear end-to-end analysis. As a result, people who want to reject your idea will essentially find reasons to reject it. So my suggestion is basically don't be derailed by this. You will be rejected, but if you're actually doing good work, you will find a way of getting it accepted at some point. Hopefully it's not too late. And hopefully there will be enough reasonable people in the world that will get it accepted. But again, you may need to spend more time than needed, unfortunately, to actually convince people, even though your initial analysis had no problem to begin with, basically. That's what it was with our Rowhammer analysis that was submitted on May 2013 to Micro, basically. Okay, so you can see many, many reasons, and you will actually need to deal with this in real life, unfortunately. People will come up with all kinds of reasons to reject your ideas. This needs more analysis, you need a better understanding of the workloads, it's not realistic, it's going to increase the complexity or cost, let us keep it simple and simple. It's not simple, so you can get both actually. It's not interoperable, that's beyond today's technology, etc., etc. Of course, these are some systems level reasons. And the last ones I like one of the most. Why change? It's working okay. I believe DRAM is working okay. Why are you bothering with this Rowhammer thing that you're not even demonstrating happens in real workloads, right? So get away, basically. That's the mindset that you can see. And this is real. This mindset is real. You will see it in every aspect of your lives, in my opinion, whenever you innovate, whenever you propose a new idea. Hopefully you will not see it, of course. Hopefully you will be in an environment that is much more progressive and receptive and inclusive. But in my experience, that environment, even if it's there, it changes over time. And as you can see, some of the environments that need to be most progressive and most reasonable have given us these comments that I have seen, which is really the scientific environments. And you can see it in other environments as well. So basically, I think it's good to be prepared for this. It's good to not derail, but actually keep doing good work. And I think Rowhammer, I don't need to tell you the story because I've already told you the rest of the story, right? The history speaks for itself. But imagine thinking that it was not published for a few years, then it wouldn't have had the impact it would have had, clearly. At some point, people would become aware of the problem, and it would always be some kind of undercurrent, right, in industry potentially. So we exposed the problem. We said, okay, here is the exposure. Now we need to solve the problem, and here are some solution directions, para being a very concrete one. And there are a bunch of 7 others. There are 6 other solution directions. Okay, so there's some food for thought. After I talked about row clone in the seminar course, one of the students that I have sent me this article saying that could Einstein get published today? And actually this article questions that basically. It's a 3-minute read according to Wall Street Journal over here. It appeared in Wall Street Journal. And this paper argues that we don't think so. And that would be terrible for human. So basically Einstein's seminal paper is on special relativity, which is the first paper that he published, is a beautifully written paper. But you can imagine thousands of different reasons today it would be rejected. And some of them actually are reasonable by today's standards because there's a lot of speculation that happens in Einstein's paper, a lot of speculation which later proved to be true. But basically, it's very difficult to get published today, even if you were Einstein, in my opinion. And that's true. I believe that this article is actually correct in its analysis of the difficulty in getting published today. Even if you have a really cool idea, a really new observation, something really that could change the world, basically. Clearly, Einstein changed the world, right? If it weren't published, imagine what would have happened.